let's continue with question number 3. This third question actually is a very simple question. So it is about entropy. It's very simple. I have a little harder question for you guys actually to work on later during the exam days, which is one of the questions in this set of the seminar notes. The purpose of this question actually is to review the equations that we already talked about in one of the. Anyways, we're going to talk about the questions about the equations about entropy, all the equations that are used when we do calculations about the change in the entropy of a system or surroundings. There are several questions that are used in calculating the entropy of a system. If I go back to the formula sheet, so I should probably erase these. So on page 1 of the formula sheet, which is again this tentative formula sheet for Chem 201 finance. On the first page, we have this equation, which is a very important equation. It's called the Clausius inequality equation. So as you see, ds is greater than or equal to dq over dt based on this equation. Okay, so the inequality in the equation. See, if I just show you guys, I've simplified it a little bit more on this page. The inequality in that equation, which shows that ds is greater than dq over t, and by the way, sorry, this d here for q must be a crossed d. So it must be a crossed d, and that actually I put here, because q is a path function, but entropy is a state function. So there should be a difference between their derivatives, and that's why we use crossed d here for q. Anyways, so this inequality here that I put here is used for an irreversible process. So the inequality in this equation is used only for the case where the process is irreversible. In a reversible process, then we can use equality, which means that this equation now can be used to calculate the change in the entropy of the system. Okay. But in a reversible process itself, so let's say the process is reversible, we already know about that. We can divide that process into some cases, two more most important cases, case 1, case 2. So the process is reversible. In case 1, it is reversible and adiabatic. So adiabatic, reversible. This means that dq is 0 because it's adiabatic. So we can simply plug this value into this equation to calculate ds. Okay, so we can simply calculate the change in the entropy of the system, which is 0 for an adiabatic reversible. For a non-adiabatic process, however, so if the process is not adiabatic, but it's still reversible, so reversible but not adiabatic, then we have two very important cases. For case 1 is when the process is isothermal. So isothermal, reversible. Of course, it's not adiabatic because it's isothermal. So isothermal, reversible. Then we can use this equation. We can integrate it because temperature here is constant. So you can simply integrate it. And as I said, q is a path function. Therefore, the integration should give you q. But s, entropy, is a state function. Of course, the integration should give you delta s. And that's why we get this equation. But don't forget, it is for an isothermal process. T was constant. In a non-isothermal process, it's still reversible. So it is non-isothermal, non-adiabatic, but reversible. What does that mean? This means, for example, this process means, for example, isobaric, reversible, or isochoric, reversible, or isenthalpic, reversible, or isosteric, reversible. So these, for example, processes are the processes that we're talking about here. It's still reversible, but it's non-isothermal. We can use this equation, but we can't simply integrate it to get this equation from the differential form. So we can't integrate it. This cannot be done here. So maybe I should use another color, a thicker. So this equation cannot be used here because temperature is not constant. You can integrate this equation only if, for example, the equation for the temperature in terms of the entropy of the system is given. For example, for this case, you can do that. T is S squared. For example, you have an equation, sorry, it's awful, I know. So T is equal to S squared. In this case, T is given based on the entropy of the system. So you can replace T by S squared and then bring T to this side and then integrate this side and then integrate the other side and then, for example, find something for the change in the entropy of the system. But when this information is not given, when there is no information about how T changes with Q, either Q or entropy, then you can't really integrate it. Okay, so you can't use it in this case. There are also some other equations. So this was all about this Clausius inequality equation on the first page of the formula sheet. There are also some other equations. Actually, I already marked them all here. So maybe I should erase these, sorry. Okay. So these two equations on top here. What are these two equations? These two equations are working equations that are used for the change in the entropy of the system. For example, in this case, based on the change in the temperature of the system and change in the volume of the system. So this is the first equation. The second equation, change in the entropy based on change in temperature and pressure of the system. Of course, you have partial derivatives here, which makes it easy for each system. For example, first evaluate this and then plug it into this equation, do the integration in different cases, and find the change in the entropy of the system. That's why it's called the working equation. What is important about these two equations here? So this first equation is that in this equation, both of these equations, they cannot be used when there is a phase transition in the system. So you can't use any of these two equations if there is a phase transition in the system. The other case is if there is a reaction in the system, then there must be some other terms added to this equation. So these two equations, to be able to use the equations for when reaction happens in the system. Because we don't have those terms, so we can't really use these two equations for the case when there is no reaction in the system. So you can't use them. So these two equations. These two equations, another important thing about them is that they are general. So other than phase transition and reactions happening in the system, other than that, they can be used in general, which means that you can use it for liquids, for solids, for gases, for reversible processes, for irreversible processes. For the case when CV is constant or not, or CV is not constant, for example, in this equation up here, or for the equation, the second equation down here, for when CP is constant or it's not constant. You can use it in both cases. Okay, and also you can use these equations in processes like isobaric, isochoric, isothermal, isenthalpic, isosteric, for example, or adiabatic. Okay, so you can use that for all those cases, all those processes. So it's a general equation. However, you can derive, if you can actually simplify these two equations for the case when in the system we have ideal gas. So ideal gas. Sorry, ideal gas. So for the case when we have ideal gas in the system, so the only pathway that we've specified here is ideal gas. And for this equation up here, for this first equation, that is derived from this first equation up here. So this equation here is derived from this first equation. This second equation here is derived from this second equation. For the case when the state of the matter of the system is ideal gas. And for this equation, for the case when CV of the system is constant. For this case, CP of the system must be constant. Okay, so it is important. CP is constant, CV is constant, and ideal gas. But we haven't specified anything else for these two equations, which means that you can use them still for both reversible and irreversible processes. You can use them for adiabatic, for an adiabatic process, for isobaric, isochoric, isenthalpic, isothermal, and other processes. Okay, so you can use them for any process that you can think of. But the only thing is, it must be ideal gas, and CV must be constant in this first equation, CP must be constant in this second equation. There is also another equation that is used in the calculations of the change in the entropy of the system. So you remember actually about these equations, these two general equations, we said that we can't use them when there is a phase transition in the system. When there is a phase transition in the system, the equation that we're using is this equation, this simple equation, which depends on the enthalpy, change in the enthalpy. Phase transition means, for example, fusion. So one of the questions in problem set number 3 was about fusion or melting. Fusion, freezing, vaporization, sublimation. So those processes that we're talking about here, phase. So there is a change in the phase of the system. For example, when ice melts to water, so there is a change from solid to liquid. In that case, you can use this equation. And this equation is the only equation that must be used, actually. So these are all the equations that we have in the formula sheet to calculate the change in the entropy of the system. Any questions so far before I go back to the question in the practice test? Okay, no question. So the question is, I just read the question here. So 1 mole of an ideal gas at 1 bar is reversibly and isobarically compressed from 25 liter to 10 liter. Is this process spontaneous? Assume CPM is 5/2 R, CP surroundings is 2.1, which means that, so this is surroundings here, and this one is for the system, okay? For the system, we usually drop the system. We usually don't put the system down here in the substrate. Okay, so this is surroundings, so it's given. And also at all times during the process from the start until the end, TC is T system is equal to T surroundings. So at all times, they are equal. Okay, so that's the information that is given, which makes it actually simple. So the question is this process spontaneous? And what we're going to do, the easiest way, is to tell the spontaneity of the process based on the change in the entropy of the system. That's the easiest way. Okay, that's what we should figure out actually in the exam. So the easiest way is to use entropy for this specific question, of course. Anyways, when we talk about the entropy and when we want to use the entropy, whenever we want to use the entropy as the measure to tell if, for example, the process is spontaneous or not, we have to calculate the entropy total of the system, the change in the total entropy of the system, okay, which is the change, I said the total change in the, the total change in the entropy, I said system, but I meant just the total change in the entropy. I'm sorry. So total change in the entropy, which is equal to the sum of the change of the entropy of the entropy of the system plus the change in the entropy of the surroundings. So total entropy change in that is equal to this sum here. What it means is that we have to calculate delta S of the system and delta S of the surroundings separately, and then plug those values into this equation, calculate delta S total, and then we can tell if this process is spontaneous or not. Okay, for the system, of course, as I said, we don't usually put sys here, system. For the system, It's a reversible process and isobaric. Okay, reversible isobaric. If I go back to these equations here that I just explained, it's a reversible process. It's not adiabatic, so it is non-adiabatic. It's non-isothermal. This means that we can't really use this equation, even though the process is reversible. It is reversible. We can use this equation, but we can't really use it because we don't have enough information about temperature here to be able to integrate this equation. So forget about this equation for this specific case. We don't really want that. What are our other options to calculate delta S of the system? If we go back to the formula sheet, we had these two equations, but for ideal gases and for the case when CV or CP are constant, we could use these simple equations. So two simple equations that we could use. One of them, which one depends actually, depends on which one is the fastest, which one gives us the fastest way to calculate what we need here, which is delta S of the system. Okay, the fastest one, because the process is isobaric, this means that we already know that P final is equal to P initial. So therefore, we already know this ratio because it's isobaric. Isobaric means constant pressure, which means that P final is equal to P initial. What about T final over T initial for the system, of course? Do we have any information about it? Of course, we have the volumes, but we also have this information here, T system equals T surroundings. Even though T system is equal to T surroundings, but it doesn't say anything about if they are, whether they are constant or not. So they're not really constant here. They're just equal at all times. They change over time, both of them, but always they have the same amount, okay, over time. So they're not constant. But still we can use this equation because we can calculate this ratio from the information that we already have in the equation, because the pressure of the system is given, the number of moles is given, the volumes are given. So why not? We can use actually that equation. So I wrote down this equation here, the equation that I just got it actually from the formula sheet. So I wrote it down here. What I need is this ratio here, which is 1, right? And then what I need is this ratio, of course, CPM and the number of moles. For this case, because ln 1 is 0, therefore it makes actually the problem simpler. So this first term goes to 0 because ln 1 is 0. What about the second case? So therefore, actually, we're left with this simple equation only. N CPM ln T final over T initial. So what I need to do, CPM of the system here is already known. So you just plug that value into this equation. The number of moles in this equation is here, which is already known, 1 mole. The only unknown in here is T final over T initial. Again, we can use this simple, awesome equation that we always use. So P final over V final, P initial over V initial is N final R. So what happens here is that the number of moles, it doesn't change. So they cancel, R's cancel. P final, of course, is equal to P initial. So in isobaric processes, isochoric processes, isothermal processes, this equation actually helps a lot. And of course, when the system is closed, which means that when N initial is equal to N final. Anyways, so we can get this simple equation, simple relation between the T finals, T initials, and V finals and V initials. Because V final over V initial, it's given, both of them, they're given here. So we can calculate this ratio here, 10 over 25, which is 0.4. That is the same ratio for TF over TI actually is the same value because they are the same. So T final over T initial is 0.4. So now that we have this value, we plug that value into this equation. That's exactly what I did here. We can calculate delta S of the system, which is negative 19.05. But as I said, this doesn't tell us anything yet about the spontaneity. For the ceramics, we have to do the exact same thing. We need another to calculate actually another piece of this puzzle here to be able to tell if the process is spontaneous. Delta S of the surroundings. What is it? So if I go back to the equations, sorry, if I go back to the question, what do we have, what information do we have about this surroundings, about the state of the matter of the surroundings? Does it tell us anything about if the surroundings is an ideal gas, if it's a liquid, if it's a solid, or if it's a real gas? If we look at all the information that we have here, we can't find any information about the state of the matter of the surroundings, if it's an ideal gas or not. So we can't find that information. Therefore, we have to assume that it's not an ideal gas. It could be liquid, it could be solid, it could be a real gas. Because of that, we can't use any of these two equations down here. So we can't use these equations. We have to go back to these equations and derive the equation that we want for this question. So we have to go back to the working equations here. But which one? In the second one, it's the, sorry, question. Okay, doesn't it say ideal gas? Okay, so let me actually check it again. Maybe I'm wrong. Okay, so if I go back to the question, it says 1 mole of an ideal gas, which means that this is the system. This is inside the system. So whatever you have, the state of the matter of the system is ideal gas. Okay, but for the surroundings, which is outside of the system, the only information that we have is this here, reversible, this reversible here, this here, and this T system equals T surroundings. That's all we have about, all we know about the surroundings based on the information given here. So nothing more. We don't know the state of the matter of the surroundings. Anyways, if I go back to the equations here in the formula sheet, so we couldn't use these two equations because it's not ideal gas. So either this equation or this equation must be used. That's these two are our only options here to answer the question. But which one? Because the process is isobaric, again, the fastest one, the best one. The process is isobaric. Isobaric means that if I use this equation, I can get rid of this differentiation here. Okay, which means that this term, the whole thing goes to 0. So I can get rid of that, which is good, actually. It makes things simpler. So why don't I use this equation here, the second equation? Therefore, ds is this, the whole equation here. So I just write it down here. So that's the equation. And then, as I said, dp goes to 0, which means that this whole second term in the right-hand side of the equation, this whole thing goes to 0. Okay. Therefore, what we're left with is this simple equation. And then what we need to do is to derive the equation for delta S. So we have to take the integral from S initial to S final. So sometimes we have to use a working equation in the exam. That was my intention here, to show you guys that actually sometimes we have to use one of the working equations and then take the integral of this equation and then find, for example, the final simple form for the equation for the change in the entropy or change in any properties of the system. Anyways, in here, so we take the integral for the left-hand side from initial to final. For the right-hand side, it's temperature. So it goes from T initial to T final. Okay, Cp over T. Sorry, actually. Okay, good. So if I take the integral, what is Cp here? Cp in here, whatever I write, actually, it's important. So all these properties, they are for the surroundings. I didn't put surroundings here. I should have put surroundings here. I'm sorry for that. But it's better to not confuse it with system. So everything here, Cp surrounding, T surrounding, dt surroundings. So surroundings for everything here, including these ones. S initial surroundings, S final surroundings. The same here. T initial for surroundings, T final for surroundings. So we're talking about the surrounding. Okay, what is Cp for the surroundings? What is it? If I go back here, Cp of the surroundings is a constant value. So this means that you can pull that out of the integral, and then it's an integral of dt over t. I skipped a step here. Then if you take the integration, you get this ln of t equation, and then from the lower limit to upper limit, so of course you get this ratio, ln of this ratio. So delta S of the surroundings is Cp of the surroundings ln T final of the surroundings over T initial. Cp of the surroundings is already known here. It's here. What about this ratio? This is the ratio of T final surroundings, T initial surroundings. Because based on the information given here, at all times during the process, from the start until the end of the process, T system is T surroundings. Therefore, this ratio here should be equal to the ratio of T F system over T I system. Okay, this ratio must be the same as that one. We already have a value actually, this value here, up here, for TF system over T initial system. So TF over T initial system, it's 0.4. Therefore, for T final surroundings over T initial surroundings, we can use that value here, and of course 2.1 for Cp, and it gives us actually, so what I did here, I'm not sure about this, sorry, I just should check this. Yes, I shouldn't put a negative sign here, sorry, it's a positive sign, so this is a mistake here, and then this must be a negative sign here. Sorry, this was a mistake. Actually, I wrote this the answer to this morning, so yeah. And then okay, so this is a negative value here for delta S of the surroundings. So delta S of the surroundings is now known, and then we already calculated delta S of the system. I called it 3, and then this one 4. We plug 3 and 4 in equation 1, which is this equation 1, to calculate delta S of total. And of course, it's not this value, it should be bigger than that. I'm sorry. You can calculate it yourself, and it gives you, of course, a negative value. It's a value. You already know that if delta S total is negative, then it is non-spontaneous. If it's positive, then it is spontaneous. The process is spontaneous. Delta S total. If it's 0, then what we call is, in fact, it is reversible, but it is non-spontaneous. It is considered as non-spontaneous, but it is reversible. It's usually called reversible or non-spontaneous, doesn't matter. So only when the sign of delta S total is positive, the process is spontaneous. So spontaneous, this is non-spontaneous, and this is just, I put reversible. Okay, so these things, spontaneous, non-spontaneous, reversible. Sure. So question number 4, which is the last question that I'm going to go over today, it's about the change in the Gibbs free energy of the system, of a reaction actually. It's about the change in the Gibbs free energy. So the question says that consider the equilibrium, which means that this reaction is already at equilibrium. At 1000 Kelvin and a constant total pressure of 2 bars, it's the total pressure. So C2H6 gas is introduced into a reaction vessel. The total pressure is held constant at 2 bar. That's the total pressure. It's held constant. And at equilibrium. At equilibrium, the composition of the mixture in mole percent are these amounts. So in mole percent for H2 gas is this, it's this amount, 20.4%. For C2H4, it's 20.4, same as H2, but for C2H6 gas, in the gas phase, it's 59.2%. Calculate Kp, the equilibrium constant, at 1000 Kelvin. That's the first question, part of the question, part A. How to do this calculation? If you go back to the notes that actually we already talked about, I think it's lecture notes 7th series, I think, 7th series. So you already have all the important points about Kp. There are three different ways to calculate Kp, equilibrium constant. One way is based on the partial pressures and mole fractions. So that is one way, which is by writing down this equation. Okay, what is this equation? So for just to simplify it a little bit more, so I replaced C2H6 by A. So I just call that A, reagent A in the system. C2H4 is reagent C in the system. For example, let's say H2 is D, reagent D in the system, which means that A here, so in a reaction, produces C and D, and they come to equilibrium at, for example, 1000 Kelvin or any other temperature. So it's always at equilibrium. Okay, to write Kp, of course, you already know that it's partial pressure of the, partial pressure of the products over P naught, which is a standard pressure. And this P naught standard pressure is always 1 bar, and it is different from total pressure here, which is 2 bar. In this case, it is different, which is important. So P naught here, Pc over P naught for one of the products, which is C2H4 product here, multiplied by Pd over P naught, raised to the power, of course, each one of them raised to the power of their stoichiometric coefficients. For both of them, it is 1. For both cases here, it's 1. It's 1 here, right? And the same as this reactant. And the reactants, they go into the to the denominator. Reactant is only A, this reagent A, C2H6. It's divided by P naught, all of them. And then P naught is the pressure and raised to the power of 1 because all of the stoichiometric coefficients, they are 1 in this specific equation. Okay, so that's the equation. We have to memorize it or because it's not given in the formula sheet. So we have to know how to write this equation in the exam, okay, based on the reaction that is given. So in order to calculate Kp at 1000, so we have to calculate each one of these ratios here. Okay, so first we start with Pc over P naught. What is Pc? The partial pressure. It's an ideal gas. Actually, it's not given here. Is it given here? It's an ideal gas, which is not given here. But actually, maybe I forgot to put that here. It's an ideal gas. Okay, so this gaseous system is an ideal gas system. Okay, so sorry, this should be ideal gas. All of them are ideal gas. Okay, anyways, I missed that part. Sorry. So the partial pressure of the system, of C for an ideal gas, we have this equation. It's mole fraction multiplied by the total pressure. I didn't put tot in the subscript here for P here, but it is total. It means total. What is P naught? P naught is a standard pressure, which is 1 bar. So P naught is 1 bar. P total is 2 bars. So they are different. And what is XC? It's 20.4%, which means 20.4 over 100. So in here, C is C2H4, and for C2H4, we have this amount here for the mole fraction. X or chi. Sometimes they show it by chi. So if we calculate this ratio, it gives us this value here. So we have now this ratio. What about PD? The exact same thing, chi D or XD multiplied by the total pressure, which gives us this amount. The exact thing for PA over P naught, okay, which gives us this amount. If I plug these values into equation 1 now, this equation here, then I can calculate Kp at 1000 Kelvin, which is this amount, at 1000, because everything that was given here, all these mole fractions, they were at 1000 Kelvin. So it is important. So all these mole fractions, the total pressure, they are given at 1000 Kelvin. So we could use this equation at 1000 Kelvin to calculate Kp. What about part B? If delta H of the reaction is this amount, calculate the value of Kp at 298.15 Kelvin. Again, there are many different ways. You already know about them. The simplest way, again, please go back to the seminar notes 7th series, and also the questions that we solved 6th series, I think fourth series, I don't remember actually, in the part that was related to the change in the Gibbs free energy. Anyways, calculate the value. One of the ways was to use the Van 't Hoff's equation. Van 't Hoff's equation, it's used when the process, the reaction, is at equilibrium. Of course, it is at equilibrium based on the information given. And it is used for the case when 1K is known already, or we can calculate it based on the information that is given. So 1K can be calculated, and delta H, of course, is given. And what we want is K at a different temperature to this first one. We already have K at 1000 Kelvin, so this K. So we can plug that value into this equation. Delta H of reaction, or I just showed it by delta HR. They are the same. Delta H not R or reaction. They are the same. I just showed it in both ways because the text shows them usually in delta HR. Anyways, so it's given. This one is given. The temperature, of course, for K2 is given, which is 298.15 Kelvin, I think. And then T1, of course, is 1000 Kelvin. This temperature, sorry, this temperature. Anyways, so in order to simplify this equation, what we always do is we take the exponential of both sides and then multiply it by K1. Of course, that's it. So if first you take the exponential of both sides and then you multiply both sides by K1 to get a very simple equation for K2 based on the other variables in the system. So if you plug those values into this equation, then what you calculate is K2, which is this value. Okay, what is important here is the units that we are using here. Okay, I just intentionally wanted to show you these units. So delta H of the reaction, the question is given in kilojoules per mole. Kilojoules per mole. Okay, delta H. When we divide it by R in here, it should have the same unit in terms of energy. Okay, which means that R here is in joules. So I just you just get this R here. So if I go back to the formula sheet, this is the R that I used here. R here, this one, this first one. Okay, so it's 8.3145 joules per mole Kelvin. Okay, so it's joules per mole Kelvin, but that one was kilojoules per mole So what I first did was I multiplied this by 1000. I converted kilojoules that was given in here to joules first, and then I plugged that value into this equation to make sure that both of them are joules, and joules per mole and joules per mole, they cancel each other. We're left with 1 over Kelvin multiplied by Kelvin down here. Then what happens is that it should give us a unitless number because it is in the exponential. So everything in here should be unitless. That's why. Okay, anyways, so K2 is calculated here. And then what is next, which is the third step, calculate delta GR for this reaction at 298.15 Kelvin. Again, if we go back to the options that we have to calculate delta GR, one of the options that we have, because the system is at equilibrium, it is at equilibrium, one of the options that we have is this one, this equation here. You can calculate delta G for when the reaction is at equilibrium based on the value for K, Kp or K, equilibrium constant. So if I go back to the question, delta G, so what we want, delta G at 298.15 Kelvin. So delta G at 298.15 Kelvin, which means that this Kp must be at 298.15 Kelvin. This temperature must be 298.15 Kelvin. What is Kp at 298.15 Kelvin? Is this second K, it's K2. It's not K1 here. This K1 here was calculated at 1000 Kelvin. So it's not this one. It must be this Kp that is used must be the same temperature as this delta G that is calculated based upon. Anyways, and this temperature must be the same. So if you plug those values into this equation, then what you calculate is in terms of joules is this amount, and then it's this amount in terms of kilojoules. So I just converted it from joules to kilojoules.